Okay, so we're going to talk today about a special type of line that we're going to graph called direct variation. And what's special about direct variation is it's a type of problem that always goes through the origin. And the origin is what we call the point 0, 0, which on our graph it's where the x-axis crosses the y-axis. So we're going to go ahead and look at our first direct variation problem. And our first direct variation problem is an equation of a line that is written in point slope form. So when I look at this is my slope, 4 or 4 over 1. And then the point that it goes through, the x value is 0 and my y value is 0. So this shows me this is direct variation because it goes through that origin point 0, 0. So I start at 0, 0 and I go up 4 over 1, right 1, up 4, right 1. And I can also go backwards to complete my line, down 4, left 1, down 4, left 1. And this gives me my direct variation graph, which is really just a line that goes through the origin. And so we can tell now if a line does not go through the origin, if it goes through another point, then it's not going to be a direct variation problem. So let's look over at our next one. This one is in slope-intercept form. So when I look at it slope-intercept form, this is my slope, -2 over 3. This is my y-intercept, 0. So I go to the y-axis at 0. Boom, I'm right at the origin, so it's a direct variation problem. And then I use my slope to move. So down 2, right 3, down 2, right 3, down 2, right 3. Or I can go backwards, up 2, left 3, up 2, left 3, and up 2, left 3. And that's our equation. Okay, so we're going to see some more, just practice a couple more. So on our next one, we have y equals -x. So I know it's going to be direct variation because there's no number added on at the end. And there is a little -1 in front of there. So remember there's no number in front of x, there's a 1. And since it has negative, it's -1. So my slope is -1. My point that I'm starting at is 0, 0. So I start at 0, 0, and I go down 1, right 1. And then I can also go backwards and go up 1, left 1. And there's our line. Okay, so on our next one, we're going to do some very same. We look at our graph, y equals 4/5 x. There is no number added on at the end. So that means my y-intercept, or my starting point, is 0. So the point 0, 0. And then my slope is that number in front of x. So 4 over 5. So I'm going to go up 4, right 5. Up 4, right 5. Or I can go backwards, down 4, left 5. And there's our graph. Okay, so we're going to delve a little deeper into this relationship of direct variation. And so what we actually have is, we've talked about our slope formula. Our slope formula is m equals y2 minus y1 over x2 minus x1. And what happens with direct variation is all of a sudden one of our points becomes 0, 0. So now this looks like y2 minus 0 over x2 minus 0, which really tells us that our slope will always be the value of any y point over the value of that x point. So I could take any point x and y and I can calculate that slope and it should be the same every single time. And so I can use that as a little trick with the table to figure out, does this have direct variation? So now I can look here for this point, y over x, and I can look at the point here, y over x, and I can look at this point here, y over x, and they should all be the same. Now, are they the same here? Well, 0 over -3 is 0, 3 over 1 is 3, 6 over 3 is 2. These are not equal, so it's not direct variation. And so I can do the same sort of thing with the next one. I can take a look at any point. So negative 10 over 2.5. Would that be the same thing as negative 20 over 5? And so I can take each point, and they should always be the same. So negative 30 over 7.5. And so now if I wanted to actually divide negative 10 by 2.5, I would actually figure out that's negative 4. Negative 20 divided by 5, negative 4. Negative 30 divided by 7.5, negative 4. And since these are all equal, check, check, this is direct variation. Now my explanation comes from the work that I showed. Why is it? Because all of these, when I compare those ratios, I get the same value. And that value is called the constant of variation. And it's really just that slope that we've been talking about. The slope every single time. And it's constant for every single point. And that's why it's called a constant of variation. So we sat there, we checked, is y over x the same? Yep, and I showed that, and it worked out perfect. Okay, so because the slope is the same everywhere on the line, we can find any point value on the line when we just know one point. So I know that they tell me that y varies directly with x. That tells me that this is a direct variation problem. So all of these, y varies directly with x, y varies directly with x. So these are all direct variation problems, which tells me that when I take y over x, so here, y over x, that should be equal to any other y over x on that graph. So when I look here, we'll find y when x is 21, y over 21. This is set up for me very nicely how to find that missing value. And so now we can use our tools from chapter 1. This is really a proportion. I can cross multiply. 9 times y has to equal, when I multiply across the other direction, 3 times 21. So now I can just divide by 9 on both sides, and it tells me that that y value is supposed to be 7. And so we're going to use that idea each time. So on our next one, y is 4.5 when x is 0.5. So 4.5, y on top, x on bottom. That should be equal to my next point. So find y when x is 10. So y over x. And now we can just cross multiply. So from here, I multiply across 0.5y equals, when I multiply across the other direction, 4.5 times 10. And now I divide by 0.5 on both sides. And I find out that y is actually 90. Okay, so let's try one more. Y varies directly with x, so y is negative 8 when x is 20. So I got that from my first point. Now we want to find y when x is negative 4. So now I'm going to go ahead and I'm going to do the same thing we've been doing. We're going to cross multiply. So 20 times y equals negative 8 times negative 4, 32. I divide by 20 on both sides. Does not look like it's going to go evenly, and that's okay. It's just how that works sometimes. So now I'm going to go ahead and reduce this. So if this is 32 over 20, I'm going to try and figure out the biggest number that goes into both. So I know that 4 can go into both. So 32 divided by 4 gives me 8. 20 divided by 4 gives me 5. So my value for y is 8 over 5. And there's direct variation. Okay, so more direct variation. Apples cost 80 cents per pound. The equation y equals 0.8x describes the cost y of x pounds of apples. Graph this direct variation. So we have several options for us. We have this equation, y equals 0.8x. We can build ourselves a table. I could say, okay, if x is 1, what is y going to be? 0.8. Well, if x is 2, what's y going to be? 1.6. If x is 3, what's y going to be? 2.4. If x is 4, what's y going to be? 3.2. If x is 5, what's y going to be? 4. Oops. Now, because I know this is direct variation, I know it's going to go through 0, 0, and I only have to graph one of these points. I'm going to graph the point 5, 4, and this will graph it for me. Now, why do you think my line only went up and to the right? Because now we're dealing with a contextual problem. We have an actual situation. Is it possible to go negative with pounds? Can I have negative dollars and negative pounds of apples? And I can't. So this part over here and this part over here, it doesn't really count. In fact, this whole area, and this whole area, because all three of those quadrants deal with negative numbers in some way or form. And the only quadrant we want is the stuff that deals with positive numbers, because in our situation, we can only have positive amount of dollars and positive amount of pounds of apples. Okay, so let's look at our next situation. We have a group of people are tubing down a river at an average speed of 2 miles per hour. The equation y equals 2x describes the number of miles y that the people will float in x hours. Graph the equation. So y equals 2x. So from here we can do a table, or we've been graphing these enough to know what to do with this. I have a slope of 2 over 1, so I start at 0, 0. I go up 2 over 1, up 2 over 1, up 2 over 1, and this will give me my line. The problem is this is not really a line, because I don't really know yet if this is going to go negative or not. So now I'd want to figure out, well, can I have negative hours? So can I go back in time, and will that actually tell me anything? It really kind of depends on the situation. I don't know enough about this. Like, I don't know if they were tubing down the river and then we started keeping track. So the time was actually, oh, we've been floating for 5 hours and now we're going to keep track. Other words, if we don't know that information, it's not safe to say that the negative values are going to make a difference. And so instead of a line, we end up with what we call a ray in geometry, a definite starting point and no end. And there would probably be an end to floating down the river. We just don't know how far down they can go, so we don't draw an end to that. Okay, and that is it for today. And we will see you next time.